Hi again. Who I am doesn't matter, but this does. Lecture 20 Electrical Hazards, Fire Hazards, and Flammable Liquids. This is all part of Safety 380 Introduction to Occupational Safety and Health. Similar to the previous lecture, covered a wide range of topics, all under that was caught and struck by. This is a wide range, kind of falling under the guises of electrical and fire safety specifically. The reading assignment, chapters 10, 11, 12, aptly because that's the topics they cover. Similar to last lecture, skim. First, let's talk about electrical safety, most commonly known as electrocution or shock. Electrocution is meant to be more of a fatal delivery of or the passage of electricity through the human body. Shock tends to be less serious, more instantaneous. Or it doesn't go through the body cavity. It's so burns are one, but really, as an electrical current passes through the human body, it's actually cooking the interior flesh as it passes through. The more sustained the time it's in there, the more damage that's done, the higher the amperage, the more energy that is transferred into the human flesh. Covered primarily under subpart S. You can also find more current or standards that were promulgated into OSHA through NFPA, or the NFPA is National Fire Protection Association, or NEC is the National Electrical Code. Sometimes they call it the Life Code as well. OSHA does have a specific health, safety, and health topics page for electrical. I should recommend you check it out. The primary goal is to prevent human contact with a live electrical line or system. Secondary would be not to allow it to arc or spark and cause a fire. I'm not going to have you do any calculations, but I want you to be aware that anybody who works in electrical safety has this stuff memorized. They're able to calculate voltage, amperage based on what they know for resistance. They can also calculate watts. So about the only time the layperson would need to calculate watts is if they were trying to designate what kind of generator to get in order to power how many 20 amp circuits or 15 amp circuits, whatever it might be. The way I like to describe electricity, it's the free flowing of electrons. And the kind of energy we get, kind of power we get to our homes, to our businesses, is alternating current. So it's a rapid, there's a frequency to it in which it's alternating back and forth. Batteries deliver direct current, or DC. So there's AC and DC. And it is just the sharing or transferring of electrons. And those electrons will, provide, energy force to have something operate, to light up, or to heat up. Sometimes you'll hear power lines give off like a hum or a sound. So it's releasing an overage of electrons through sound. Sometimes it's heat, sometimes it's light. The big arcing is just sort of the release or a non-direct connection. You can have arcing. And it says here, as it flows through media, if you're pushing too many electrons through at once, there's friction and heat, and that's what's dangerous. And so the design of electrical systems, the circuitry within your home, within your business or public place, is designed so that the circuit will cut or break if the electron flow exceeds the design elements of that circuitry, in order to maintain the safety, the protection factors that are in place. So the insulation. So if a wire is allowed to carry too many electrons, it will heat up, it will melt the insulation, the wire becomes exposed, and now it can either arc, spark, or energize a metal chassis of a piece of machine or something, and then the next person touches it, becomes part of the circuit. So the design is it breaks it at the source. So if you start drawing too much, it'll break the circuit. If you have a broken circuit breaker, or you rely on something that's lower quality, not certified by Underwriters Laboratory, it may not break the circuit, and therefore then you'll have damaged equipment. You can also have arcing, and whenever I do an inspection, I always check out all outlets for any evidence of arcing and sparking. There'll be like burn marks, basically. Yeah. An arc flash or an arc blast, and this is not to be confused with what I talked about in the last lecture when it's regard to a welder's exposure to their eyes when they look into the arc when they're arc welding. They call that arc flash. That's the burn in the eyes. An arc flash event is when you have an incidental connection between two power sources, and whatever is making that connection explodes. So it could be a tool, a hand tool. It could just be another electrical part, whatever it might be. But it instantaneously vaporizes metal. It gives off a very powerful shock or percussion wave. It gives off a lot of it's just a rapid expansion of energy, and you'll have a video where you can see what happens. These cause serious injuries. It's scary to watch, and I mean, it's metal can actually infuse into human flesh if you're not properly protected. So you always want to work on electrical systems with them de-energized, because if you're working on them energized, it's possible that you could incidentally create an arc flash. And anybody who's doing any work around a system that's live need to have the proper PPE, which is all identified under NFPA 70E. And then whenever you go past a power panel or electrical panel, you'll see this warning sign bottom right, the warning of what is required for protective clothing for people who are going to work on it. This is not something to be taken lightly. This is there's physical damage, there's human harm and human toll, and it can be very, very costly. So it's best to de-energize, but when you can't, you have to have someone who's an expert and expert electrician, and then someone who's wearing the proper PPE and using the proper procedures. You don't mess around with electrical. This is a home electrical panel. You can see all the circuitry, you can see the lines coming in, you can see the main breaker for the house, and then you see a bunch of colored wires going away. This is an older system, probably using conduit. Looks like there's a conduit coming out because these have multiple red, green, blue, yellow. Looks like some other colors too. In newer homes or newer installations, they're probably using like solid Romex, like either a 20 amp system or a 15 amp system. A 15 amp system uses 14 gauge. A 20 amp uses 12 gauge. That's what, those gauges are designed to handle that much, those many electrons to flow through. The white insulation is typically the neutral, and the black or the red is usually the hot or the energized line, and then green is ground. That's usually what you see when you go into these cabinets. Now, I don't recommend you ever go into these cabinets, and if you ever trip a circuit, what you're supposed to do is stand aside or adjacent to it and then reach over with one arm, and you should probably have a leather glove on or something to protect it, and then turn it on. You should not stand right in front of it because it could explode right into your face, and that would be an arc flash, and that would be really bad. I have here right below here, these are different safety devices. Some are GFCI, or ground fault circuit interrupters. We have insulated tools to protect the user. We also have a lockout tagout kit. We saw that in the last lecture too. There's a lot to electrical. I like doing electrical. I kind of fancy myself as a journeyman electrician. I haven't sat for an exam yet, but I've done it enough on home remodels. I call in the experts. They do the inspection, the city inspection, to make sure I've done all the installations correct. And that's sometimes when I find out, well, you have to do this extra level of safety, which I'm more than happy to do. I find it really satisfying and interesting. That's my favorite of all home improvement trades, electrical work, followed closely by carpentry. But there's a lot you can do. And I've got a lot of testing devices I also use. I don't have them in front of me because I actually use them for a mock OSHA audit for my design class just yesterday, and we're going again tomorrow. So we're checking polarity on the outlets. We're checking for grounds. We're testing GFCI. We're walking through shops and we're testing all these things, and we're also inspecting the circuit breaker panels to make sure there's no unguarded access that a person could get accidentally shocked. Shifting gears. So we've got fire safety and fire protection. There's several ideas behind this. There's several approaches. One is we want to prevent it from happening. Two, we need a detection system if it is happening. And three, we need a warning system in order to evacuate or alert if it's happening. So those are the kind of the three things. And they can be interconnected, of course. You also need to have a plan for what to do if there is a fire. And if you're going to have your employees fight a fire with a fire extinguisher, you have to give them fire extinguisher training annually on how to properly use it, how to properly fight a fire. I think more importantly is, what size of fire can you fight? Because sometimes a fire is, you don't have the capability to suppress it with just a typical fire extinguisher. So therefore, the fire extinguishers really are meant to make sure that they can get a clear access, clear exit access, basically is what I'm saying. And you need to have designated pathways to exit. That's why you see the lit exit signs. Only those should designate which way you should go. And some companies actually have to change the construction of certain hallways in order for it to meet the minimum requirement to be an escape or an exit pathway, that it will hold back fire on the other side of it long enough so that the place can be completely evacuated. The doors that open can't open to another hazardous thing. Some people just, we'll just let them exit this door. But the door opens to like a highway. You can't do that. That's an exaggeration. But you can't open it to another hazard. You also can't lock them from the inside. There have been companies who, we don't want workers sneaking out this door, or we don't want them stealing and taking things out. So they bolt and chain exit doors, and then you need it, and then nobody has the key, and people get locked inside. And so you should train people on, if you want them to fight a fire, teach them how to use a fire extinguisher, how to recognize what they can fight. If not, then use the fire extinguishers as a means to clear exit ways, to clear pathways to get out. And also you should have some form of being able to count or acknowledge who made it out. You know, a gathering place, an attendance. There's a lot of things you should do to ensure that everybody can exit safely and there's proper communication. And then I think it's every year company or every building needs to be inspected by a fire marshal or a fire inspector. And what they're doing is they're just making sure, like, he's inspecting a standpipe. The standpipe feeds the fire suppression system. Sometimes you call them sprinkler systems. Sometimes they're a little bit more complex. You can see down on the bottom there. It just depends on whether they all operate at once, so one turns on, all turn on, or they have water in the system already, and so it just releases, or it's a dry system, and so when it opens, the air rushes out and drops the water in when it reaches it. It just, these are costly systems, and the owner of the building needs to decide what they want to do. And as my friend who does this as a living has always said that, well, what you have to do is assess what type of fire. Because if you have big fire, you need big water. Big water is very expensive. If it's little fire, then you can do little water. But the problem is you should never then change the use or storage in that space that would require big water. That's the term he uses. And I've got all kinds of references here for you. The idea with fire, just like we talked about Ohm's law, that was earlier. You don't have to use it, but I want you to know what Ohm's law is. Similarly, we've got the fire tetrahedron, and we've probably grew up knowing that you need fuel, oxygen, and heat to have a fire. But now, with the different types of fire suppression technologies, we now add in chain reaction to finish off the tetrahedron, so four-sided, because there are some suppression chemicals that actually prevent the rapid oxygen reduction reaction to stop. So it's not controlling oxygen, it's not controlling heat, not controlling fuel, it's actually stopping the chemical reaction. But a lot of these systems, what they're attempting to do is either cool it down to the point where it won't burn, suppress the oxygen, so that's typically a liquid, and then or controlling the fuel or mitigating the fuel. And depending on what type of apparatus you have that could catch fire, you may want to select something more sophisticated, like for sensitive electronics. They may use like a halon system. So it's dropping a gas that stops the chemical reaction versus suppressing with water, suppressing with foam, or suppressing with like a powder, because it would take a lot to clean and repair everything. They're just trying to minimize the damage. But those things are more expensive because you also need to be able to isolate the room and then vent it afterwards. There's a lot more than just, spraying water. Okay. And then once you have the access points for the escape, you should also put up maps. I know whenever I go into like a hotel, I know it's on the back of the door. I always look at it just to get an idea which way I should go. That's just me. I've got a lot of videos on this because human nature is to return to what you know. So if you enter a building through certain doors, in an emergency, you will attempt to exit through those doors, even though there are multiple exits in the front of the plane, side of the plane, and the back of the plane. You'll tend to go to what you know. So if you're ever in a situation in which a crowded building needs to be evacuated, fight the urge, grab as many people as you can, and hit one of the exits that nobody else is using, and everybody is stampeding towards the one that will cause injury. So sometimes you'll see that there are manual activation of fire alarms. Sometimes it's automatic because they have a smoke detection or heat detection. In places where there could be loud or have people who have hard of hearing, you have to have a flashing strobe. Yeah. You should practice your fire drills. I know people are like, oh, fire drill, I don't have time. Do it anyway. Because you just never know when you're going to need it. It's better to know where to go and not need it than to need it and not know where to go. I sound like your mom. Another thing is with the sprinkler heads that you see in buildings, the bulb, which is actually, I think, a fusible link, that it melts and then it releases the water pressure or the pressure that's behind it. You can see they've got, based on color, what temperature it will, I guess you want to say, fail at and allow things to go through. So this one is at 155 degrees Fahrenheit. Why would you want it at purple, you might say? Well, maybe there's work going on, and during that work, temperatures may get up above 300 degrees. But it dissipates or whatever. Well, you don't want to set off a sprinkler alarm when it's just everyday type work going on. So it depends on the type of operation you have going on. So you have to know what's going to go on before you select the proper fire suppression system and detection system and exit. Sometimes you'll see the NFPA diamond, and it kind of indicates what are the hazards or what's in it. And this is more, we're leading into flammable liquids now. And I look at these also for DOT placards. So if I'm behind a tanker truck and I see it's hauling something that could explode or, reacts to water or something like that, I will try to not be behind that person. But if I look up and there's really no danger and it's hauling like chocolate or milk or something, then by all means, I'll just stay behind it. No big deal. And so sometimes you'll see these placards on doors as well, where they store chemicals. It's meant to inform firefighters, emergency people, what's in there. When it comes to combustible liquids, you probably are more familiar with gasoline, but there are things that burn much more easier in workplaces. These things need to be contained in, I was going to say contained in containers, but jugs, so you can transfer it to something else safely. And safety cans are made of metal, and the nozzles are metal, and they have a fail-safe close, so like a spring-loaded open close, and it has a pocket in the back that allows air into it so that you don't have glugging, because glugging when you're filling, and you do that with your cheap gasoline cans at home that are plastic, and it sprays, and you want to minimize that. Another thing too is when you have a metal can, metal nozzle connecting into other metal tank, it dissipates any sort of potential for static electricity. Because when liquid flows through something, it can create a static charge. And I'll try to provide a video. I think I already have one, but sometimes they change them up, in which, like in the wintertime, especially up north, somebody will go to a gas station, they'll start the filling gas, and then they'll go sit in their car and they're wearing a wool coat and wool mittens. And them just sitting down in the car with the wool seat touching this, their wool coat touching the seat, can create a static charge because the air is really dry too. So when they go back to touch the nozzle, they're carrying a static charge. So as soon as they touch the nozzle, there's a small arc, small static spark that could actually ignite the fumes that are coming out of that, which you can never see, you can smell, because as you're adding a flammable liquid to a confined tank, there has to be a volumetric displasion. That volumetric displasion is the vapor that's in the tank itself. And so as you're filling your vehicle, there is a vaporous cloud coming out of there that could ignite. Now, could it actually go into the gas tank and blow up? Probably not, because we have upper and lower flammability limits. There's not enough oxygen. It's too concentrated with the vapor to actually ignite the tank itself. But what do people do when they see something ignite? They freak out. Pull out the nozzle and spray it around. I'll kill it by putting more fuel. No, that's bad. Don't do that. It's better just to let it go out and try to blow it out right away. So I've got a lot of terms here. The classification for flammability is based on flash point and boiling point. Liquid doesn't burn. The vaporization of a flammable or combustible liquid is what burns. So the more volatile it is, the more readily that it vaporizes, the more flammable it is. The more likely it is to create a cloud capable of not only being ignited, but to sustain a burn. Secondarily, if it has a very low boiling point, it also tends to be more volatile, and therefore, if something is heated to its boiling point, it becomes very flammable. That's the way it works. So we need to make sure that we're storing this stuff properly, we're labeling this stuff properly, we're handling this stuff properly, and if we're transferring it from something to something else, they need to be electrically bonded and grounded to mitigate the potential for, ignition through a spark release. Here we've got someone actually filling a safety can with a 55-gallon drum. The 55-gallon drum is actually, see, you got a connection here. This is the ground line. A ground line is simply something metal that gets driven into the ground. And so it's clipped on. So it's grounded through that line. And then here, there's another line to the front, and it's bonded to the can here. So no chance for a static potential to grow. Ignite it. Covered a lot of stuff. Didn't even cover BLEVs. Boiling liquid expanding vapor explosion. So the tanker cars that are on the tracks, when those go off and those ignite, it'll only burn the vapor that comes off. But the thing is, as it's heating, it's starting to make the water or the flammable liquid inside it to boil. And so all it takes is for the container itself to completely get damaged, and then there'll just be a huge rapid expansion of the vapor, and and I'll try to have a video of that too. That's called a BLEVy. Those are very dangerous, which is why you'll see sometimes firefighters, all they're doing is soaking the container to keep it cool enough not to have a massive release. And it looks like they're not even fighting it, but that's what they're doing. They're trying to prevent the BLEVy, and they're trying to get it to burn itself out if they can, trying to limit cooling it down and let just the vapor burn off if they can. So I gave you a lot of things. Check out the chapters. Check out the videos. The videos do a really good job of showing all these hazards I'm talking about.